Assalamu alaikum. So in previous class we discussed about task analysis, and I already hinted you in my previous class that we'll discuss about distributed cognition in this lecture. So let's dive into the details. So in discussing a human-computer interaction, there's often a tendency to look narrowly at the user interacting with the computer, or slightly more broadly at the user interacting with the task through some computer. But many times we are interested in zooming even further out. We are interested not only in the interaction between the human, the computer, and the task, but also in the context in which the interaction takes place. So in this lecture, we are going to look at 4 different models or theories of the context surrounding HCI. We'll focus primarily on distributed cognition, which is one of the dominant theories on the interplay between multiple agents, artifacts, and contexts. We'll also touch on 3 significant theories: social cognition, situated action, and activity theory. So, distributed cognition. So, cognition on its own is interested in thought processes and experiences, and we naturally think of those as occurring inside the mind. But distributed cognition suggests that models of cognition should be extended outside the mind. This theory proposes expanding the unit we use to analyze intelligence from a single mind to a mind equipped with other minds and artifacts, and the relationships among them. So let's take an example of this. Let's consider a hard addition problem. I may tell you to add the numbers 1238 and 6437. Okay, can you add that one in your head? Most of you will say, no, we also can't even remember the numbers you just read to me. But assume if you have a pen and paper there, and using those, you can easily write down the numbers. Okay, using that, you can now do the calculations by hand, and the answer will be 7675. Now, did I get smarter? When I grabbed the pen and paper, not really, not by the usual definition of smarter at least. But the system comprised of myself, the pen, the paper, is a lot more than just my mind on its own. The cognition was distributed among these artifacts. Specifically, the paper took care of remembering the numbers for me and remembering and tracking my progress so far. So instead of adding 1238 and 6437, I was really just adding 8 plus 7, 3 plus 3, 2 plus 4, and so on. Now, one of the seminal works in distributed cognition research is a paper from the Journal of Cognitive Science from 1995 called How a Cockpit Remembers Its Speeds by Edwin Hutchins. You might recognize Edwin Hutchins' name from our lecture on direct manipulation and invisible interfaces. He was one of the co-authors there as well, along with Don Norman. This is one of my favorite papers, in part simply because of the very subtle change in emphasis that we see in the title. We tend to think of remembering as a uniquely human or biological behavior. We describe computers as having memory, but we don't usually describe computers as remembering things. Remembering is more of a human behavior, but the paper title twists that a little bit. It isn't the human. It isn't the pilot remembering, it's the cockpit remembering. What is the cockpit? The cockpit is a collection of controls, sensors, and interfaces, as well as the pilots themselves. The paper title tells us that it's this entire system: the pilots, the sensors, the controls, and the interfaces among them that do the remembering. The system as a whole, or the cockpit as a whole, is remembering the speed, not just the human pilot or pilots in the cockpit. No individual part in isolation remembers what the system as a whole can remember. Now let's just see some of the snippets, or let's just see the concepts of this paper. So in order to understand the application of distributed cognition to the cockpit, it's important for us to first understand what challenge it's addressing. The technical reasons for this are a bit complex, and I strongly encourage reading the full paper to get the full picture. But to understand the simplified description, I'll give here. Here's what you need to know. So when a plane is descending for landing, there exists a number of different changes the pilots need to make to the wing configurations. These changes are made at different speeds during the descent. When the plane slows down to a certain speed, it demands a certain change to the wing configuration. The speeds at which these configuration changes must happen differ based on a number of different variables. So for every flight, there is a unique set of speeds that must be remembered. That's why the title of this paper is How a Cockpit Remembers Its Speeds. Speeds, plural. It isn't just remembering how fast it's going now. It's remembering a sequence of speeds at which multiple changes must be made. The configuration changes to the wings must be made during the descent at narrowly defined times. That creates a high cognitive load. Pilots must act quickly, and mistakes could mean the deaths of themselves and hundreds of others. So, how do they do this? First, the pilots have pages that contain the speeds for their descent based on different parameters. The cockpit itself has an entire booklet of pages like this. So, we know that the cockpit has its pilots who are responsible for actually reasoning over things. But that booklet forms that cockpit's long-term memory of different speeds for different parameters. Then prior to the descent, the pilots find the page from that booklet that corresponds to their current parameters. They pull it out and pin it up inside the cockpit. That way, the sheet is accessible to both pilots and they are able to check one another's action throughout. This becomes one form of the cockpit's short-term memory, a temporary representation of the current speeds. At this point, we have to attribute knowledge of those speeds to the cockpit itself. If we were to isolate either pilot, they would be unable to say what the speeds are from memory. But without the pilots to interpret those speeds, the card itself is meaningless. So it's the system of the entire cockpit, including the pilots, the booklet, and the current card that remembers the speeds. Then, as the pilot begins the descent, they mark the different speeds right on the speedometer with these little speed bugs. The speed bugs tell them which speeds to remember in a way that can just be visually compared. When they see the speedometer pass a speed bug, they know it's time to make a certain change. This is like the working memory for the cockpit. The short-term memory stores the numbers in a way that the pilots can reason over, but the speed bugs on the speedometer store them in a way that they can be very quickly just visually compare. They don't need to remember the numbers themselves or do any math. All they have to do is visually compare the speed bugs to the current position of the speedometer. So, what do we see from the system as a whole? Well, we see the long-term memory in the book of cards, we see a short-term memory in the card they selected, we see a working memory in the speed bugs on the speedometer, and we see decisions on when to make configuration changes distributed across the pilots and these artifacts. No single part of this cockpit, not the pilots, not the speed bugs, not the cards, could perform the action necessary to land a plane on their own. It's only the system as a whole that does. That's the essence of distributed cognition. The cognition involved in landing this plane is distributed across the components of the system. This is a deeper notion than just using interfaces to help us do tasks. The important thing here is that these different interfaces serve cognitive roles in the system. Now let's just discuss about the cognitive load and its relationship with the distributed cognition. Distributed cognition is deeply related to the idea of cognitive load. Recall, the cognitive load refers to your mind's ability to only deal with a certain amount of information at a time. And we have already discussed about this in our class when we did some examples about remembering and recalling. Distributed cognition suggests that artifacts add additional cognitive resources. That means the same cognitive load is distributed across a greater number of resources. Artifacts are like plugging extra memory into your brain. Driving is a good example of this. Sometimes, while driving, your cognitive load can be very, very high. You have to keep track of the other cars around you. You have to keep track of your own speed to monitor your route planning. You have to make predictions about traffic patterns. You have to pay attention to your own level of gasoline or electric charge in some cases. You might be attending to something in your car as well, like talking to your passenger or keeping an eye on your child in the backseat. It can be a big challenge. A GPS is a way of offloading one of the tasks navigation onto another system, and thus your cognition is now distributed between you and the GPS. Turn on cruise control and now it's distributed across the car as well. You're offloading the task of tracking your speed to the car. Every task you also de-artifacts decreases your own personal cognitive load. Now let's analyze a simple task from the perspective of distributed cognition. Here we see a user paying some bills the old-fashioned way. For each bill, she pulls it off the pile, reads it, writes a check, and puts them together in a stack on the right. Where do we delineate this system? What are its parts? So take a moment and think of an answer which you can provide with respect to what the user is actually doing and how the distributive cognition plays a part in this. Well, we are interested in any part of the system that performs some of the cognition for this user. While the chair, table, and light overhead makes this possible, they aren't serving any cognitive roles. Morgan herself, of course, is, and two piles of bills are too. They are an external memory of what bills Morgan has already paid and what she still needs to pay. This way, she doesn't have to mentally keep track of what bills she has left to do. The bills themselves remember a lot of the information for her as well, like the amounts and the destinations they need to be sent to. What about the pen and checkbook? That's when things start to get a little bit more tricky. The checkbook itself is part of the system because it takes care of the record keeping task for this user. Checkbooks create carbon copies, which means Morgan doesn't have to think about tracking the checks manually. The pen is a means of communicating between these systems, which means it's part of our distributed cognition system as well. Now let's see cognition as a lens. Something important to note is that distributed cognition isn't really another design principle. Distributed cognition is more of a way of looking at interface design. It's a way of approaching the problem that puts your attention squarely on how to extend the mind across artifacts. We can actually view many of our design principles as examples of distributed cognition. For instance, when I set up my computer, I don't think about it in terms of distributed cognition, and yet I can use distributed cognition as a lens through which to view this design. For example, I always have my sticky notes on my desktop. That's a way of offloading having to keep track of my daily schedule in working memory. It bugs me if I have a teleconference to attend or somewhere I need to go. In fact, I rely on this so much it gets me in trouble. It doesn't keep track of where I need to be for a given meeting, and if I fail to keep track of that in working memory, I might end up at home when I need to be at University of Sin. I even view trivial things like a clock as an example of distributed cognition that prevents me from having to keep track of the passage of time manually. The point is that distributed cognition is a way of looking at interfaces and interface design that focuses your attention on what systems as a whole can accomplish as opposed to individuals on their own. Now, distributed cognition is a fun one to reflect on because we can take it to some pretty silly extremes. We can go so far as to say that I don't heat up my dinner. The system comprised of myself and the microwave heats it up. And I offload the need to track the time to cook on to my microwave's timer. And that's perfectly valid way of looking at things. But what we are interested in is places where interfaces don't just make our lives more convenient. We are interested in places where the systems comprised of us and interfaces are capable of doing more, specifically because those interfaces exhibit certain cognitive qualities. The systems might perceive, they might remember, they might learn, they might act on our behalf. In some way, they are offloading a cognitive task from us. And as a result, the system comprised of us and the interface is capable of doing more. So reflect on that a bit. What is the place where the system comprised of you and some number of interfaces is capable of doing more than you alone, specifically because of the cognitive qualities that the interfaces possess? Almost any interface on the computer can be analyzed from the perspective of distributed cognition. But right now, I am most interested in my email. My email is an unbelievable extension of my long-term memory because whenever I see anything in email, I know I don't actually need to commit it to my own long-term memory. It's there. It's safe forever. And if I ever need to find it again, I'll be able to find it. Now finding it might take some work sometimes, but rarely as much work as manually remembering it. For me, I also mark messages as unread if I am the one they are waiting on, or if I need to make sure I come back to them. And so, my email is an external memory of both all my communications via email and tasks that are waiting on me to move forward. Now, distributive cognition is concerned with how the mind can be extended by relations with our artifacts and other individuals. Because we are interface designers, we probably focus most of our time on the artifacts part of that. After all, even though we are designing tasks, the artifacts are what we are actually creating that's out in the world. But the other part of distributed cognition, distributing across individuals, presents a powerful opportunity as well. This used to be far more important actually. Before the days of GPS navigation, a different form of navigation assistance existed. It was your spouse or your friend sitting in the passenger seat, reading a map and calling out directions to you. And while mobile devices and artificial intelligence may have replaced humans in some such systems, there are still lots of places where the role of distributing across humans is crucial. Here's an example of this in action today. At different MOOCs, Massive Open Online Courses platform, they use a tool for managing projects called Jira. It breaks down projects into multiple pieces that can be moved through a series of steps and assigned to different responsible individuals. The entire value of Jira is that it manages distributing tasks across members of a team. Thus, when a project is completed, it is completed by the system, comprising the individual team members and Jira itself. Now I'll end this lecture at this point, and we'll be discussing the social cognition part and the activity part in the next part of this lecture. Thank you.